Okay, hi, welcome to everybody to this MCA invited talk. It's a great pleasure to introduce Davi Maximo. He's professor in the mathematics department at the University of Pennsylvania. His research interests lie in the fields of geometric analysis, PDE, and geometric topology, where he's a renowned specialist and has made outstanding contributions. So we are happy to have him today. He's going to talk about the geometry and topology of three-manifold with a positive scalar curvature.
Well, thank you very much for the introduction, Guillermo, and thank you, the organizers, for the invitation and for, making the change to online. I mean, I wish I was in Argentina right now. It's been a long time. That would be nice, but hopefully the near future. Okay, so today I want to talk about some basic questions about the geometry topology of manifolds of small dimensions. And as a guide, I want to basically just do a quick slide in dimension 2, just to kind of set the kind of questions we'll be looking at to generalize. So basically, in dimension 2, there's only one curvature condition which is the Gauss curvature of a surface in this case. And I'm going to assume that I'm interested in positive curvature. So let's say that we have a surface, a closed surface with a metric of positive curvature. And by, uniformization theorem or Gauss-Bonnet, you can, from that local condition, you can actually infer some global topological information that, that has to be a true sphere. So no tori, no genus at all, just from that local curvature condition that is a pointwise positivity condition. But you can also infer from that a little more. So for example, if you want to quantify things a little, instead of just saying that it has positive curvature, if you say that the curvature at least some number kappa, which, a positive number kappa, then you can actually say a few more things of the geometric nature. So for instance, you can estimate the diameter from above and also the area of the surface from above. So in other words, in at least in this two-dimensional picture, we get the following: that positive curvature implies a topological restriction, or in this case of classification. So we know what the topology must be, but we also have what I call here in this work geometric smallness, that somehow how positive the curvature is controlling that you have to be small in some geometric sense, and at least in the sense of the diameter and the area. Okay, so that's what I would like to look at in 3 dimensions. And I guess one natural curvature condition to look at there would be maybe sectional curvature or even Ricci curvature. And indeed, even if you look at Ricci curvature, there's been, I guess by now classical results that a metric with positive Ricci curvature, you can determine the topology. So by the work of Hamilton, who introduced Ricci flow in the 80s, these manifolds, they must be diffeomorphic to a spherical space form. And you also get, by Bonden-Myers and volume comparison, a similar geometric smallness. So that's for the Ricci curvature in 3 dimensions. But what I want to look at in this work, or I want you to understand, was what kind of geometric smallness you can get for a weaker curvature condition, which is the positive scalar curvature condition. Okay. Okay. So let's see, what is the scalar curvature, by the way. I realized there could be people in the audience maybe that don't necessarily work on these things. So let's assume throughout that we have a 3-manifold, and the scalar curvature is bounded below by some positive number lambda, capital lambda. So if you I guess want to crash introduction to scalar curvature, I think that the sort of way that I prefer is the following. So you have your metric, which is this movably varying inner product, and you want to write it in coordinates somehow. And you see that depending on the change of coordinates that you do, the inner product has looks a little nicer. You might diagonalize at a point and so on. But in a way, the best you can do is that you can write your inner product Gij. You know, if you really work on your coordinates, you get the best one, which is in some sense this what a normal coordinate system. The metric will look like the Euclidean one, which is minus a third, and then you have this quadratic error here. So in other words, this is the curvature, right? This is what is obstructing you to make the inner product, a smoothly varying inner product, to actually look like just a fixed one. And the scalar curvature manifests when you take this Taylor expansion of this smoothly varying inner product locally, and you calculate the volume. So I take a ball of radius epsilon with this metric G, and a ball of radius epsilon, this metric delta, so epsilon small, and I get this expansion here in terms of epsilon. So basically, I'm having a metric of positive scalar curvature is giving me a condition infinitesimally on the level of volume, right? Of like having a, slightly less volume than the Euclidean one. So it sounds like a very soft condition, and it is. I'm gonna, kind of mention that at least locally, it's a very soft condition. And by the way, this definition, I find it very cute, but I never seen a fact about scalar curvature that you can prove using this definition. But anyway, so one thing about scalar curvature, which motivated our work, and I think a lot of the current developments, it's that it has this duality, which is that it's weak in some sense. So locally, scalar curvature is very weak, and I'll show some results. But there are times when globally it's a strong condition, it's a very strong restriction to have a metric of positive scalar curvature. And somehow we were interested in somehow the borderline case of that. So when, what can you say, how much you can push, this positive scalar curvature condition to get information about, for instance, geometric smallness. Can that be something that you can attain? Okay, so let me tell you why I say that scalar curvature is weak. So for example, if you give me any function on a manifold that is negative at some point, right, then I can prescribe a metric G that has that function as the scalar curvature. So a scalar curvature is a pointwise condition, is the pointwise the infinitesimal growth of the volume, right, up to second order there. And yeah, so you give me a function. All I ask is that it's negative somewhere. I don't care about anything else. Then you can do that. And this is done by, basically it's a PDE result. For using that, you can actually put that any manifold with boundary.
Sorry.
Yeah, question?
May I ask you something? Yeah.
Sure,
In the
sure,
first system, M must be compact or any M?
Good question. I think you could do any with any M. If you have non-compact, you even have more flexibility.
Right.
So,
yeah.
And if you use B, you can. I mean, if you use the first part, you can actually then prove that any manifold boundary, as also admit a metric with positive scalar curvature. You just double the manifold and you pick a function that is just a little negative in one of the halves, right, and positive on the other half of the double, and that would give you the desired metric. Another flexibility is the connected sum of manifolds of positive scalar curvature also admits a metric with positive scalar curvature. So basically, you are adding like a cylinder, right? Like when you try to glue these two things, and the cylinder has very positive scalar curvature. So you can do that. So that's why, you know, one has the tendency to say that, okay, it's a weak condition. You compare with all the curvature conditions, it, you know, it looks very weak. You can't dream to do that with like Ricci curvature. Like the prescribing Ricci curvature problem is very hard, for instance, right? It has very strong restriction on the fundamental group and so on. So it's definitely way more flexible than any other of the classical curvature conditions. Okay, but surprisingly, you know, it's, you know, there are also results that point to its strongness, how strong it is, and that's what makes it interesting, because when you can take such a flexible curvature condition, you can actually prove something restrictive, right? It sounds very interesting. So, for example, over the years, people discovered invariants for you know, topological obstructions for manifold to admit a metric postscalar curvature. For instance, there are some that come from these this theory of the A-hat genus. It's the theory of Dirac operators on manifolds that admit a spin structure. There's also some restrictions found using minimal hypersurfaces. So it has some global consequences. And another area where scalar curvature plays a huge role is the, you know, the area of general relativity, where it's the Lagrangian density of this Einstein-Hilbert action. So this curvature plays like an important role as a density in general relativity. And in fact, for three manifolds, if you combine the work of Shen and Yao and Perelman, you can actually classify compact manifolds that, you know, closed manifolds that admit metrics of postscalar curvature. So if you have one of those, it has to look like a connected sum of a sphere, right? Some S3, and then maybe some spherical space forms. You can have some of them, and also S2 cross S1s, okay? So the way basically that this was obtained was that Shen and Yao in the 70s, they discovered that having a metric of postscalar curvature on the three manifold imposes some restrictions on the fundamental group. So they were able to classify their fundamental group in the 70s, right? And then obviously there was the Poincare conjecture still open back then, which was that, you know, even if you know that the fundamental group is trivial, you don't know what the manifold is, right? And that was solved by Perelman. So if you put those two together, you get the topological classification. Okay, so maybe I can say a little bit how that goes, because it will come back to the talk. So for example, if you take a three tors, this is the classical example, right? Like the idea is to basically the observation that they made is that if I have a surface on a three manifold postscalar curvature that minimizes area up to second order, these kinds of surfaces we call them stable surfaces. So if you have a manifold with a stable minimal surface and the manifold has postscalar curvature, then that has to be a sphere. Now there are some, you know, other cases, it could be an RP2, depending on whether the manifold is one-sided, you know, the surface is two-sided and so on. Like, but if we restrict to orientable manifold, two-sided surfaces, then, you know, it has to be a sphere, okay? And how can you use that? So basically what they did then is that they found this area minimization scheme, where if you have a manifold that has a very complicated topology, then you can find surfaces there of higher genus that will minimize area, okay? So that would contradict then the fact that it has postscalar curvature, because the postscalar curvature is putting a restriction, right, on the topology of the surface that can minimize area, okay? So, okay, so I have, you know, a basic picture here, for example, for the three tors. Basically what the minimization scheme like. So if the three tors, you start with a two tors which is incompressible. So in other words, the fundamental group of these two tors here in blue injects on the fundamental group of the three tors, And it turns out that you can start minimizing the area of these bootars. You start moving it, right? In that class of all the surfaces that has the same action on the fundamental group level. And they prove that that process of minimizing area will find one always that is stable. So it minimizes area up to second order for local perturbations. And basically that's a contradiction. That's because, you know, if the three torus has a metrical positive scalar curvature, this cannot exist. You can only find spheres. So via minimization. So basically, you know, that's how the result goes. Okay. All right. So you see here that minimal surfaces, they play a role, and they'll come back later in the talk. Now, the question then for us is that, okay, so if I have a manifold of positive scalar curvature, three manifolds, so we know that the topological, I mean, this was the starting point for our study, was that, okay, we know the topology. So positive scalar curvature in 3 dimensions, it gives you the topological classification. Now, what about the geometric smallness? Can we do something? Now, one has to be careful there because, like I said, because topology, positive scalar curvature is so soft, and you can do connected sums, for example. So then there is no hole to make the manifold small, right? In the sense that you can start taking connected sums, and at least the diameter, right, will be as large as you want, okay? And also the area will be as large as you want, right? I mean, the volume of the manifold. So, but, you know, and there is actually a more complicated construction you can do, which is the you can take well, this is general. You can take any manifold M. Oops. You can take any manifold M, and you cross it with a true sphere. And if you just make, okay, so this is a manifold, might have negative curvature. It can be, you know, any manifold you pick, like, you know, this, as long as it's closed, right? There is you can cross it with S2 with a very small radius, and this guy will have a metrical positive scalar curvature. Okay, so in other words, really, you can't say much about geometric smallness because this could be anything in general, right? But it sounds like you have here up to codimension 2, there is nothing you can do. But this sphere, the scalar curvature somehow is telling you that this sphere has to be small if you want to do this kind of construction, right? So so there are these observations that somehow that, you know, codimension 2 smallness in the world of positive scalar curvature manifolds, and indeed that's what we're going to try to do. So that, you know, if you give me a 3 manifold with metrical positive scalar curvature, so imagine something like this here. This is not the drawing of a surface of genus, I don't know, 8. This is, you know, just like you could take manifolds with positive scalar curvature, you start, you know, gluing them up with connected sums, and you can get these very complicated 3 manifolds, right? But somehow this connected sum, you're kind of following a graph in your construction. So basically, you know, there is this graph skeleton underneath this complicated examples that can be generated via connected sums. So you put these two things together, the codimension 2 and these constructions, there is actually this very clear question of Gromov, which is that if you give me a manifold with positive scalar curvature, then there must exist a polyhedral complex of codimension 2 and a continuous map from the manifold to that complex, such that the preimage of every point in the complex has bounded diameter and bounded area. So this question is what I mean by codimension 2 smallness. So up to some, you have no control just from the scalar curvature alone. You have no control what this polyhedral complex looks like. Okay, so we have no idea. This could be very complicated, but that's all, in the sense that there is a map from the manifold to that, and then the pre-images of the map, the scalar curvature does control that. Okay, so this is somehow the geometric smallness that we are after. Okay, so some more as a generalization. Okay, so are there any questions so far? Maybe I can state the result and the next slide, and then maybe it will be a good point to ask questions. So basically what we did recently with Evgeny Lyukomovich from University of Toronto is that we prove that given a closed three-manifold with positive scalar curvature, well, a uniformly bounded scalar curvature, there exists a metric graph gamma, okay, and a continuous map from the manifold to that graph, such that for every point on the graph, the pre-image will have controlled area and control diameter, and also control genus. It's because it's going to be two-dimensional, so you can find the Euler characteristic and so on. So yeah, so this is our version of saying that these manifolds are small in this sense. So up to this codimension 1 to codimension 2 graph, which can be huge, can be the scalar curvature has no say with any graph gamma that you want, basically. But you give up that graph, knowing the geometry of that graph, then you can control everything else. Okay. And we have another version where instead of getting a map from the manifold to a graph, we can actually construct like a Morse function. I mean, this is just preferred in some applications, I think, of these foliations of manifolds. And we're just basically gluing in the pre-images to make it level sets of a Morse function. But there you do have to the statements that you control for each level set. We control the area, diameter, and genus of the connected components of the level sets. The level sets are not going to be connected necessarily, and the result is only for the connected component. Okay. Right. So any questions about our result? What we want to prove? Okay, so the picture is something like this, right? You give me the manifold, I find this graph. Okay, it can look strange, and but we have this control. The fibers are controlled. Okay, now so let me focus for the rest of the talk at the proof of theorem A. I want to kind of tell you what's the strategies, what we had to do to accomplish that, and theorem B basically follows from theorem A. So so let's forget about the Morse function for now, and stick to this map from the manifold to a graph gamma. Okay. Okay, so so the proof will be done in several steps. Basically, the starting point for us was this observation that whenever I have a positive lower bound on the manifold, I get geometric smallness in terms of area and diameter of certain special types of minimal surfaces. In other words, surface of index 0, which are the stable ones, and surface of index 1. What is the surface of minimal surface of index 1? Well, that's basically a surface that is not stable. So in other words, there are directions where you can make the area smaller, right? But essentially, there's only one such direction. So that's why we call index 1. So for example, an example of that is like an equator, an S2 equator inside of S3. So that's a minimal surface. It has index 1 because you can push the equator in one direction, and you make it, the area will go down. But essentially, that's the only deformation that you can make that will do such thing. Okay, so it turns out, and this has been known for a while, that whenever you have a minimal surface inside a three-manifold with positive scalar curvature, you do have geometric smallness of that surface, right? So our idea was like, okay, how do we propagate that? So somehow if I take this minimal surface and I start foliating the manifold, somehow I can propagate the geometric smallness of that surface along, right, these leaves of this foliation, then I would get the foliation of the manifold by surfaces which are geometrically small, okay? But then, there are several problems in doing that. So for instance, the first thing we'll do then is we're going to take the manifold and we're going to cut along all these surfaces. So basically we're going to look around the manifold and we're going to be looking for surfaces, minimal surfaces that have index 0 or 1, and we're going to cut the manifold along that, disjoint surfaces, and we're going to get several manifolds with boundary, okay, this way. And on each of those boundary components, once we cut, right, we're going to start to use mean curvature flow and some metric geometry ideas to propagate from the boundary, right? So this will be manifolds with boundary because we cut along this minimal surface. So it's a manifold with boundary, and the boundary are minimal surfaces of controlled geometry. Now we want to flow in, this information we want to propagate inside, okay? And essentially this process will be the process that will construct the graph, okay? The graph gamma. Okay, so so I do want to say the mean curvature flow is a natural tool for this because it's whenever it's the gradient flow for area. So if I have an area bound of a surface and I somehow start flowing, right, I will be propagating that area bound, right? But we also want to bound the diameter, and for that, the mean curvature flow really doesn't tell you anything nice in terms of what kind of control you will get. So we have to mix it up with these two ideas. But okay, but before we dwell into that, that's step 3. I want to tell you a little bit about step 1, which why you have the geometric smallness, how this sectional curvature bound propagates, okay, to minimal surfaces.
Davi?
Okay. Yeah.
Davi?
Hey, how are you? Yes.
How are you? What kind of subsets are these pre-images, these fibers?
Okay.
They are not smooth necessarily, right? Or
well, they're small in the sense of area and diameter.
No, smooth.
Oh, okay. Good question. Yes. No. So most of them are smooth, but but some are not. Yes. So especially when you have a vertex of the graph, you can have some, piecewise smooth thing.
So you can control smoothness by taking pre-images of certain points.
Yes.
Regular
yes.
points.
And yes.
Oh,
yes,
great.
Indeed.
Okay.
Yes. Yeah.
Okay.
So I'll hopefully be able to make them more clear soon. We'll see. But so the this slide here, which is like that first point, it's basically why do you get from scalar curvature? How do you get that scalar curvature implies geometric smallness for a minimal surface, right? So somehow you get this step there, reduction. So basically it comes from this observation. So whenever you have a minimal surface and you consider a variation, let's say something like you take a function phi, right? And you try to move the surface along phi times the normal vector. Well, if you take that variation and you calculate the area along the variation and you take two derivatives of that as 0, because again, we want to look at minimizing area up to second order, you get this expression here. So you get the gradient of that function along the along the surface. You get the Ricci curvature of the ambient, and you get the second fundamental form A of your surface. Okay, but where is curvature? Scalar curvature is here, and how does stability, plays a role? So basically, what stability does for you is telling you that this quadratic form is greater or equal to 0, right? For every phi. That's what stable means. You try all directions phi to make the area smaller, you up to second order, and you can't. This is greater or equal to 0. So I just take this gradient term and I integrate by parts. So that quadratic form having a sign is telling me that this operator, Laplacian plus Ricci normal direction plus a square, has a non-negative first eigenvalue, lambda 1. Okay. And what is the connection then with scalar curvature of this? So the connection is that, okay, if I take now, whenever I have positive scalar curvature of this ambient manifold, and I consider the metric u squared times g, okay, where is g? So in other words, I take the ambient metric of the manifold, I restrict to the surface, and I multiply that by u squared, where u is the first eigenfunction of this stability operator. Well, this new metric, which is going to be a conformal metric, is going to be a metric of positive Gauss curvature. So scalar curvature on the ambient implies that, and scalar curvature on the ambient and a stable minimal surface implies that I can do a conformal change to the metric of the hypersurface. This is even the general in the dimensions, but in this case, let's say a surface inside a three-manifold, and that surface would have a metric of positive Gauss curvature. Okay, so in particular, it has to be a sphere. Topologically, it has to be a sphere. But also, you can say things like, whenever I have that the scalar curvature is instead of bigger than 0, I get that it's bigger than some positive number, lambda, then I'm going to have that this metric u squared times g has a metric of positive Gauss curvature which is bounded below by some lambda over a constant, right? And then I get the geometric smallness also for this conformal metric. Now it takes a little work to say, okay, this metric u squared times g is small, but you can actually prove that g is also has to be small. So you can bound the area and the diameter of g. Okay. So that's the connection, the starting point for the result. Okay. And basically what you get is you get these two results here, is that whenever I have a metric, a manifold positive scalar curvature, a stable surface there is a version with boundary. So whenever I have boundary, I can bound the distance from a point, right, to the boundary of the surface. So it's stable with boundary. It's stable, no boundary, I get a bounded diameter. And index 1 and no boundary, I get another bounded diameter also. Okay. And similarly, you also get that ambient with a positive scalar curvature, lower bound. Then you can bound the area of a stable surface from above or an area of a index 1 surface from above. So we have these two things. Okay. So that's the starting point. And then next, what we do is we start decomposing the three-manifold. So we'll basically start looking for these minimal surfaces. And we're going to cut until we find this pieces where we can't cut anymore. And I'm going to call them geometrically prime. So what is a geometrically prime manifold? There's a manifold with boundary, where I have no closed embeddable surface inside. There is one boundary component, which is a surface of index 1, or mi-convex. And I'll explain that why I'm allowing this mean convex here, you could just think that S1 is a minimal surface of index 1 for now. And the other one is all stable surfaces, which all have to be two spheres, okay? And so we prove this result that if I have a manifold with positive scalar curvature with a bumpy metric, what it means a bumpy metric. So basically, you see our result about geometric smallness is stable under perturbation. So in other words, if I have my metric and if I perturb the metric a little bit, the result is still true, right? So I make the metric bumpy so that I don't have, you know, it's a technical term. Basically, what it tells you is that you don't have like one parameter family of surfaces, because that would be bad. If you imagine you have a cylinder where you have infinitely many slices, right, which are all stable minimal two spheres. So which one do you cut? You know, so you have to cut all of them. You know, you keep cutting forever. But if you just perturb the metric a little bit, that round cylinder becomes, you know, a little bend, and then you have only one surface there that you cut. Okay. So with a bumpy metric, no one parameter family of minimal surfaces, then I can cut in at most n pieces such that each piece has genus at most 2, and m minus the union of the surfaces are all geometrically prime regions. Okay, so let me show you a drawing. So the idea is basically to you know, let's say that this is our manifold, and on the first step I look for stable minimal surfaces, and I start looking at them, and basically what I find is it's a bunch of disconnected minimal true spheres. And now I have these pieces, right? And these are manifolds with boundary now, and the boundary are stable minimal true spheres. And what we do then to find the index ones is we use a min-max procedure, and that you know basically says that when I have a three-manifold with Hegardt splitting of smallest genus, I can isotope that Hegardt surface to a surface of index 1, and the result is the technique is robust enough that you can apply to manifolds with stable boundary, which is our case. So basically, I'll then look at the Hegardt splitting of these pieces, and I will do a min-max, and then I will isotope to index 1 minimal surface, and this will be the picture I get. So if I cut the red surfaces, which are stable, and the blue surfaces, which are index 1, I get that, you know, disconnected two pieces like this one's here, okay, which are geometrically prime. Okay, so now to prove our result, basically, we know by the results for minimal surfaces that these surfaces, the blue and red minimal surfaces, they have bounded area and bounded diameter, and also bounded genus. Okay, so what remains to be done is to basically take each of these pieces. Let's say we take this piece here, this middle piece here, and we're going to prove the theorem to this piece. So basically, we take, you know, a manifold that looks like this. We have an index 1 surface here, which is this S1, and then we have minimal two spheres as the other boundary, and we want to get this foliation, let's say, right, that will have controlled area and diameter. Okay, so let's work with the area first, because whenever I want to propagate area, in this case here, there is a very fine tool, which is mean curvature flow. So what do I do? Well, I have my S1, which I know the area is bounded by most like 32 pi or something, like 32 pi over root lambda, this guy here. It's a minimal surface of index 1. So if I push it into the normal direction, it will move inside here, and it would be mean convex, right? So in other words, I'm going to have a region here where the mean curvature points this way. Okay. So what I'll do is I'll start flowing by mean curvature. And the mean convexity is nice because it's telling me that this flow, it will be monotone. Okay. You know, because mean curvature flow, you are deforming a surface in the direction of the mean curvature, and mean curvature flow preserves mean convexity. So you will, you know, you have a monotone, so which is perfect for us because we want a foliation. If we did not have mean convexity, this would be a problem right off the bat, because you know I will start flowing the surface, but maybe the surface starts to wiggle around, right? It's not monotone. But a mean convex mean curvature flow, we have monotonicity. Okay. The other thing about mean curvature flow with mean convexity, which is crucial for us, is that, well, in general, mean curvature flow can behave, you know, very widely in terms of you can have singularities happening. And, you know, in this case, actually, in our case here, for example, this picture, they're expected to happen because we want this thing to split off and somehow start to foliate and end in these three spheres. So we want to start from the blue surface of index 1 and finish at the blue spheres. So we need this to disconnect somehow. And what does it mean to disconnect? It's to, you know, for singularity to happen, like the curvature blows up and this pops off. So there is a theory that does this for us. Is you know, the mean curvature flow with surgeries. And basically what happens in the mean curvature flow surgeries is that I start flowing my surfaces, and I set some parameters, which basically says I'm gonna set these parameters saying that whenever the curvature gets this large, okay, I will go my manifold, and I'm gonna look for the regions of high curvature, and then I'm gonna cut the regions of high curvature, okay, and then glue in things of smaller curvature so that I can reduce the maximum of the curvature of these surfaces, and then I will start the flow again. And then if, you know, so I reduce the maximum of the curvature, and then I flow again. That might increase. Well, I do it the process again, and I do it again, and do it again. Now, to do this, you need to know that you need a result that the regions of high curvature, you have to know what they look like. And lucky for us, there's a whole theory of you know, I think started by Brian White, then, you know, Simon Brendler worked on it, Hasselhofer and Kleiner. There's a, you know, great theory for mean curvature flow surgery. I should put Huisken in there, Huisken, Sinestrati. That, you know, we can choose these parameters, and this is what will happen. This curvature will get large, like here, this picture. The large regions, they're going to look cylindrical. So, you know, you need like a cylindrical estimate like that. And because they look cylindrical, you can put like caps. When you put the caps, right, you basically, you know, you cut and you place caps. You still have high curvature here, maybe at these points. But if you look at a region where you have a high curvature disconnected component, right, it's not as high as it was, but it's still high. But I'm gonna keep the connected components right after I do this process, where the curvature is still, you know, where I still have like curvature of a smaller order. So this one gets discarded because here the curvature is everywhere large, so I can discard that. Okay. Okay, so what does the mean curvature flow with surgery does for us? It basically, you know, this is some sort of legalese, if you want to use, you know, mean curvature flow. These are the curvature quantities: the trigger, the neck, and the thick. So the trigger is the trigger. It's like whenever the curvature hits that, you're going to do the surgery. The neck is basically a much smaller level, but it's sort of like how the curvature is going to look like near these caps. So it's going to be like neck. And the thick is the rest of the curvature, like in other regions which are not involved in the surgery. So, you know, so every time it hits the trigger, I do a surgery. Then I look at the connect, I place with caps that have curvature at the level of the neck, right? So I brought it down, the curvature, but then I look at the components, and if there is a component that has no thick curvature, like in this one, this one here has no thick curvature, I just throw it away, okay? And then I keep going. Now, the nice thing about this process is that, okay, so here, you know, maybe there will be a neck, it's gonna pop off, and it's gonna, you know, converge to these three spheres. Now, another thing of the level set flow is that because it's monotone, there is you can prove that it will foliate this region minus this discarded component. Okay, so if I flow this by mean curvature, this will give me a foliation of this geometrically prime region, except for these discarded components. But these discarded components, they are very small, they're cylindrical, you know, so which, you know, I know that the geometry, how it looks like. So I can come and fill them by hand, you know, in terms of a graph. So for example, in this surgery here, why do you get a graph? Is because basically I had a mean curvature flow. So let's say that these surfaces, they were shrinking, right? So it looks like this. And then I have a surgery process. So the surgery process, it's split off in two surfaces that now they're gonna flow by mean curvature. So this is gonna flow inside here on its own. And independent of this, is gonna flow inside here on its own, okay? And maybe I have the blue sphere. So maybe there is a blue sphere here on the boundary, right? There's another one here. So it will shrink to those guys. So this is the blue spheres, let's say. So what happened here is that then I split off, right? So that's why I work with a graph. But then I have these discarded components that are not being foliated. So basically I have to come here by hand, and I have to foliate them by hand. And maybe I can use like some small edges like that. So the graph actually is going to look something like this, you see, and these will be points that I'm shrinking down, okay, to foliate this area. So this is how you get, guys, the area bounds, basically using mean curvature flow. Now, I should say a few words about how do you actually can also get with, you know, this process, you also get to control the diameter, okay? And one problem is that with mean curvature flow alone, you cannot get a diameter bound that depends only on the scalar curvature. You may say something like this: giving me a manifold, I can do this construction, and there will exist a constant for which these surfaces have bounded diameter, of course, right? But okay, but that's not, that doesn't depend on the scalar curvature. So maybe there is a sequence of manifolds with the same lower bound on the scalar curvature where you have to get a larger and larger diameter to make this work, right? So, and we want geometric smallness coming from the sectional curvature alone, right? So how do we get that? And for that, we have to interfere with the mean curvature flow a little bit. So basically, what we'll do is that whenever we are flowing, okay, and we're going to predetermine a bound for our diameter, and whenever we're flowing by mean curvature flow, if for some reason this gets too large, I'm going to cut the we're going to cut that surface and change it a little bit, okay. So the idea comes basically from this, which is that we can prove that if I look at the equidistant surfaces, so now instead of taking S1 and flow by mean curvature, I'm looking at equidistant surfaces from S1. And if I look at those surfaces, they all will have bounded diameter, okay? So this is the trade-off. If you want area bounds, use mean curvature flow. If you want bounded diameter, you can look at equidistant surfaces. But the equidistant surface, you don't control the area. One, you see, you kind of have to mix the two up to get both at the same time. And the proof, it's a, you know, it involves a little trick, but it does uses minimal surfaces. This is what the nice thing about the proof. You have to find this curve and you solve the Plato problem, this guy here, this green guy, is going to be a stable disk, and you're going to use that. You have bounds for that. But in the interest of time, let me skip the proof of this. Okay. And finally, what we do, the way that we mix them up is with this result, that if I have a surface, a connected surface that is contained between two equidistant surfaces, then the diameter of these is bounded. So I have a bound on this equidistant surface, diameter of this equidistant surface. I have a bound on the diameter of this equidistant surface, and they're not too far apart. They're like 10 pi over root lambda apart. Then I can bound the diameter of this surface. And by the way, here should be clear. I mean, if there was some confusion because I may have not said so, this is the extrinsic diameter that we bound. Okay, this will be false for the intrinsic diameter, right? But it's the extrinsic diameter bound. So and basically using this is how we proceed. We now go back to our surface S1, start flowing by mean curvature. And then I look whether it's trapped between the equidistant surface. So this is the closest point to S1. This is the furthest point apart. And whenever they get further apart than 10, they start to get further apart than 10 pi over root lambda, I'm going to come here and I'm going to cut this right in the middle, right? Because you see, up to this point, by this lemma, I have a diameter bound of 40 pi over root lambda. But maybe a second later on mean curvature flow, this will start being too far, like the closest point to S1 and the first point of S1, they start to get further than 10 pi of root lambda apart, and then I might lose this applicability of this lemma. So I have to come here and I have to cut these with curves, glue in minimal surfaces, and then start doing a mean curvature flow again from these pieces. And okay, and one more that we have to deal with here is that somehow this process ends, that I don't have to do infinitely many of these interferences of mean curvature flow. So there's some things to arrow out. And another interesting thing is that when we glue this surface, which is this green guy, you see, I glue this green guy, the genus here is still 2 on this side, but the genus on the other side might have increased to 4. So this is an issue that we had to figure out, that the genus, could increase, and that could, could potentially harm the statement that we wanted to prove, which is that the genus of these surfaces is most 6. Okay, so I stop here, guys. Thanks for your attention. Thank you.
Thanks, Davi, for such a nice talk. So if someone has a question, feel free to unmute your microphone and turn off your camera, or write in the chat.
Hi, Davi.
Yes, hi. Hey, Max. How are you?
Fine, thank you. Thank you for the talk. Davi, about your main theorem, you have examples. Can you hear me?
Yes.
I'd like to know about examples with, hygienus, for instance. You have some examples that you construct?
Okay, so the problem for us is basically the question of the genus, right? It comes from this final step where we have a mean curvature flow that we are about to lose the diameter bound, right? Then we have to cut the surface with a curve like this light blue here. We cut it, and now naturally, what we would like to do, right? Naturally, I would just cut it here and I would glue a disk, a minimal disk, stable minimal disk. That wouldn't increase the genus at all because it will be a disk. Now, if this will be stable, this will be stable. So what does that mean? It means that if I desingularize this to both sides will be mean convex. So the nice thing about the stable surface that you desingularize, right? It becomes mean convex. So that's what we want. So this will flow this direction, this will flow that direction. The problem is that when I take this curve and I want to glue in the disk, right? I don't know how much area that disk will have, you see, because we have it could potentially, if I just fixate myself in the topology. I say, okay, I want a disk, right? And I try to glue it here. Well, the problem is that the area could go above our bound, you see. It's strange, but we don't have a competitor for the disk, for the path problem that we know the area of, to say that, oh, the disk that minimizes area has such area. What do we have as competitors here are these two connected components of the red surface, this one and this one. So we pick the one with less area, which in this case is the one that has the genus, you see? So now what I do is I take this curve and I take the red guy and I minimize area in the isotopy class. And when I do that, the genus could survive. It could become a disk, but it could survive too, right? And now when I glue this green guy and I look at now the both sides, this one, this will have genus too. The area is okay because you see the area of green is less than the area of this red. And so then this new area is going to be less than the total area of before, right? So I get the area bound. But the problem here is that the genus goes up by 4. So, it could go up to 4 because when I do this. So we actually have to show that this cannot happen, when you in 3 times in a row. Basically, that's what we show. So that you get a genus at most 6. You can do this construction genus at most 6. But I would expect that that you don't need genus, more than 2, because it would be 2 and below. But it's a problem. Like even if you take a S3, right? It's an interesting question. Take the 3 sphere and you take a curve there and you try to solve the Plateau problem. Why does it have to be this? It's natural, right? But maybe there could be some surface of some genus that has even less area, right? So, yeah.
All right, thank you, David. Nice talk.
I wish we were in Argentina eating churrasco right now. Parrillada. Next time.
Sure.
I would like to make a question if time permits.
Okay, let's see.
Okay, Davi, you said that you can control the area if you have a stable minimal or index 1 surface, right?
Yeah.
Even when you have boundary, you said that in the stable case you can control the area.
No. The boundary is for the distance. It's in the so there's 2. So let me go back. So there's 2 results. So yeah. So the boundary is distance. You can control the distance to the boundary.
Oh, all right.
Yeah. But the area is only closed.
Okay.
Right.
So but in the index 1 with boundary, can you say something about that? Also, what is the problem you are considering in the boundary case? For example, stable is fixed boundary.
Yeah. No, you have the surface, right? You have the surface with fixed boundary. Then you want to say that you have a surface there. You want to say that just because it's stable, you can bound the distance from an interior point to the boundary. Right. Now, if you want to bound the area, it's actually there's the problem is that you can have a long boundary, right? So you could have a curve which is big, and then you solve you minimize the area, right, for that boundary curve. You get something you're gonna have something with large area. I think what you can try to control there, you can try to control the area of a stable surface boundary, but you have to account for the boundary length. Maybe you can bound the area using the boundary length, so that if the boundary length is big, the area gets big, right?
Okay. Yeah.
But yeah.
All right. Thank you.
Are there any more questions? Okay. If not, we thank Davi again.
Thank you, everyone. Thank you.